Okay, so we're just continuing on in this whole lake ecology thing, and we're going to specifically look at gas solubility. As I said, nutrients we've kind of covered fairly extensively already, so I'll refer to them. But again, what I want you to be aware of and know is your nitrogen and phosphorus cycles. For instance, nitrogen, its main component, its main source of nitrogen is from the atmosphere, and that's how you get the nitrates in the water and everything else. Whereas phosphorus comes from soils. It's basically geologic in its origin. Most of your particulate phosphorus is going to be from non-point source runoff type situations. Most of your dissolved phosphorus you're going to find coming from wastewater treatment plants, because our feces and especially our urine are full of phosphorus, dissolved phosphorus and nitrogen. Okay, so let's have a look at some of the gases over here. First of all, gas affects several things. I had to remember what EC25 was. All right, there's only a certain amount of gas that can be dissolved in the water, and that's going to be inversely proportionate to your temperatures. And if any one of you has ever opened a beer and then left it for like 5 hours and then come back to it, and it's down on Edisto Beach there, and it's like 93 degrees and it's 100% humidity, you don't want to touch that beer because it's flat. It just doesn't taste good, apart from the fact that it's warm. The other thing that happens is that when gases at lower temperatures, when gases are more soluble in water, what you actually find is that your electrical conductivity, EC25, actually increases, or EC. And that's because there are more there are more soluble ions in the water, especially your bicarbonate ion. And we'll look at carbon dioxide. You know, one of the things I was looking at data, and I just couldn't understand why electrical conductivity in some of the warm southern waters that we have here was so much higher in the winter. It's like, you know, stuff coming down from Charlotte. Are they putting salt on the roads? No. And eventually it kind of struck me that, yeah, it's temperature related. You've just got more bicarbonates and other inorganic molecules dissolved, gas molecules dissolved in the water in the winter than in the summer. And that makes your electrical conductivity higher. All right, so let's look at major sources of dissolved oxygen. Well, you guys have been here before because that's what we did in the Streeter-Phelps model, right? So tell me 2 major sources of dissolved oxygen. Major source of oxygen in the water, DO in the water.
Wind turbulence.
Turbulence. So wave action, and that's gonna it's basically gonna allow diffusion and dissolution of water from the surface, right? Okay. And the other one would be photosynthesis. Okay. So plants are going to take in carbon dioxide and exude, that's not breathe out or whatever, produce DO. Okay, so those are the 2 major sources of DO in the water. Of course, the sinks of DO would be things like what? What would be the major sink then?
Biological oxygen demand.
Yeah, biological oxygen demand, especially when you get to the surface, not the surface, to your benthic, your benthic oxygen demand. But fish breathe and all of those things, so that's part of it. But decomposition is one of your biggest sources, you know, all this organic material. Okay, here we go, major sinks. So diffusion of oxygen, let's just draw this. So oxygen actually can leave the water, especially if the water is saturated or supersaturated. And again, we find in southern waters, and I think up north as well, if you've got a lot of biological activity in your lake, all of a sudden you're finding 10, 11.5 milligrams per liter of DO, and it's like, dude, saturation DO sat is about 10, so how come there's more oxygen in the water? Well, it's super saturated. These little algae plants are producing more oxygen than the water can hold, and it's coming up now. It's not bubbling out, but I've seen that as well. It's pretty interesting. Have you seen that? I'm sorry, I'm picking on you, but
from macrophytes, but not from algae, I don't think.
Yeah, I don't know. I can't remember where I saw it, but I saw it basically on the surface, where we had our DO was higher than DO.
Oh, you mean, okay, yeah. Seen it. I've seen readings that were super saturated.
Yeah. Really? I didn't know that could exist, so that was pretty cool. So, diffusion of O2 out, a water column. What they basically distinguish is this water column respiration. So that's all the critters in the actual water column itself. What we call, the amount of water, the water from the surface to the benthic layer, all right? And then, of course, you have sediment oxygen demand, SOD, and often this is quite high. At that low level, you're going to find, especially in eutrophic lakes, that's where you're going to find, whoa, there's not much oxygen there, especially in the summer when your biology starts to warm up. Okay? So, we've talked about oxygen variability over 24 hours versus over a year. And let's go through that again. Remember, we talked about bathtubs and hills. Okay, so let's look at that again. This is my O2. That's a little bit sharp there. My O2 variability here. If I had to look at this, and maybe let's not have those shoulders there. Let's do this. My axis over here, my time axis, would this be a day and this a year? Or would this be a day and this a year? I don't know if my question is too obscure.
The latter one.
This one would be what?
A day, lowest during the middle of the day.
And why would that be?
Higher temperature of the water.
Higher temperature of the water would be higher or lower oxygen?
Lower oxygen.
Lower oxygen, okay. Okay. I hope I don't...
There's also greater photosynthetic activity in the middle of the day.
Right.
So I guess it would depend on which of those two factors is driving
holds out. So your logic is impeccable. What we do find, though, is typically that the biological factor prevails in the summer, certainly in these southern eutrophic lakes, where you have a lot of algal photosynthesis, and you have this burst of DO. Your DOs go up, and then they kind of drop overnight. But what you also find then is in the winter, you have very high DOs, and then over the summer, they drop. And this drop over here is more to do with your saturated dissolved oxygen. And that's basically inversely proportional to temperature. So typically, annual, this would be dial days. Okay, makes sense? Okay. Let's talk a little bit about some other gases. We've talked a lot about oxygen, but let's talk about nitrogen and CO2. I guess the only thing about nitrogen, again, nitrogen is very much, 79% of the air is filled with nitrogen. it's pretty inert. The only time, and this is kind of cool, the only time you would find nitrogen being a problem is in the tail races of dams, of impoundments. Is as the water goes down there, often nitrogen gets entrained into the water and it becomes super saturated, and it gives fish the bends. So you'll find often fish swimming upside down. Now, I've not seen that myself. So nitrogen, I mean, it's inert. In general, nitrogen in the water is at saturation. But apart from, and because it's inert, you've got nothing specifically using it unless you have, say, a nitrogen-fixing algae or something that's using it. And we don't have that much in terms of, unless it's blue-green algae, right? Blue-green algae is going to be nitrogen-fixing. So nitrogen's inert, it's going to generally be more or less at saturation, whereas oxygen is being consumed all the time, so it's going to be typically less than saturation. Does that make sense? All right, the next thing is this whole idea of CO2. And when we talk, you might have heard of the term inorganic carbon, CO2, inorganic. So CO2 is given off when we respire. CO2, we've got 350 to 400 parts per million of CO2 in the atmosphere. So CO2 is going to come into the water like that. Fish are going to breathe and take DO in, breathe CO2 out. And then your sediments are also going to emit CO2. Okay. One of the things about carbon, we talked about it earlier on, was this, let me go here and make sure. I think it's over here. Is this equation over here, the Sodapop chemistry equation. H plus CO3 2 minus H plus HCO3 minus, that's your bicarbonate, H2CO3, that's your carbonic acid, CO2 aqueous, CO2 gas, plus H2O. This equation drives a lot of the water chemistry that we have. And often this equation is very much dependent, or not often, but where this equation settles down is very much dependent on pH. So if we draw this continuum of pH from 0 to 14, what you'll find is that there are certain states that this inorganic carbon is going to be resting at certain temperatures. So going back to that little diagram, the inorganic equilibrium, bicarbonate. Bicarbonate, basically 100% until you get to a pH of about 5.
Isn't that the carbonic acid?
Sorry, excuse me. H2, thank you very much.
And just in general, is this is being driven by availability of the H plus species based on pH, right?
Exactly.
So
you're
so
measuring
it's directly
pH.
related to your measurement of pH.
Right. But yeah, thank you. I think that's essentially the chemical explanation. Yeah, because it's not the abstract idea of pH itself, but pH is the inverse log of the concentration of moles of H plus ions. So you're absolutely correct. So the amount of H plus that's available given your dissolved or your inorganic C or carbon dioxide, that's what's going to drive it. So carbonic acid at about 5, that's going to drop off to about zilch at about 7 or 8. Okay, so the inorganic carbon that you're going to find in the water at pHs of less than 5, and once you get to a pH of 4 or 3, the majority of, or all of that inorganic carbon is going to be in the form of carbonic acid. Okay. Now what happens as pH rises, okay, so is this guy called HCO3, the bicarbonate. And if you remember earlier on in the class, bicarbonates were by far the most abundant anion in aquatic systems. And I'm kind of a chemical engineer that dealt with carbons, anions and cations. Bicarbonates were not in my sort of vocabulary. And so I had to kind of relearn this over here. So essentially, when we look at most systems, the majority of what we see is bicarbonate. So if you're seeing inorganic carbon in waters that have a pH of somewhere between 6.5 and 8, it's all going to be in the form of bicarbonate, probably close to 100% over there. Okay, so going back here, availability of H ions, not quite as much availability of H ions. And then what happens over here, as H ions become more and more scarce, we're going to actually find that CO3 ion, the carbonate ion. There's no hydrogen, and I'm not sure if that what that carbonate. I don't know what the charge is on that one, but the carbonate ion then begins to predominate. So at a pH of 12, any inorganic carbon is going to be carbonate. Okay. What we see in ambient, in sort of natural waters, we're seeing this animal over here. Does that make sense, guys? Okay, good. And you're absolutely right.
That helped it make a lot more sense, actually, when I was thinking about it. I was like, why does this happen?
Yeah.
Because pH.
Yeah, it is, yeah. So it's not that abstract idea of pH, but the availability of that hydrogen positive ion. Okay, so major sources of and sinks of CO2. I think we've been through it where we can understand that, but maybe looking at some of the sinks is that CO2 actually also precipitates. If you've got a lot of calcium, will precipitate as calcium carbonate in the benthic zone, in the sediment. It'll precipitate with magnesium, so magnesium carbonate. And then it can actually, if you have lower pHs, those calcium and magnesium carbonates may dissolve again. When we talk about calcium and magnesium carbonate, what water property are we thinking of as well? There's a water property.
Hardness?
Hardness, yeah. Remember, calcium and magnesium carbonates, those are what constitute hardness, okay? So you need inorganic carbon in the form of carbon dioxide forming with calcium and magnesium, okay? And then, of course, sinks would also be photosynthesis. And then they talk about the conversion from one thing to another, which is pH dependent. Really, that's abstract. It's dependent on the availability of your hydrogen ions. Okay. In terms of our water chemistry, the major ions, the major anions we have, bicarbonates, by far the most in fresh water are going to be around about 74%. Then we have sulfates, about 16%, chlorides, and SiO2. Now there's a little footnote in that thing, is that nitrogen or nitrates and phosphates are way, way, way much less than all of those anions. And yet, those are the guys, because they are the limiting nutrient, say if phosphorus is the limiting nutrient, even though it might be way less than 1% of all the anions in the water, if it's there in excess, that is going to be the thing that causes eutrophication. So that's kind of a cool thing. So look at that footnote. It's pretty important. Okay. The availability or the amount of CO2, what they say here is alkalinity, acid neutralizing capability, acidity, carbon dioxide, pH, total inorganic carbon, and hardness are all related and are all part of that inorganic carbon complex. And that's kind of a neat drawing to see over here, this Sodapop chemistry drawing that you have. All right. So I'm going to skip, because we've seen phosphorus already. We've seen different, I'd like you just to go through that, make sure you're familiar with that. But I don't think there's much point in our talking about limiting nutrients and things again. But it's important in lake ecology, because if we understand what our limiting nutrients are, we can then at least begin to address the cause. You know, for instance, if your limiting nutrient in a particular water body is nitrogen, not much point in you spending $100 million in a plant to take phosphorus out. You know, you want to go and deal with the nitrogen. So that's kind of the idea there. Questions so far? Okay. When we talk about limiting nutrients, or not limiting nutrients, we're going to kind of move on to management of lake water. And there's something called the TSI. So this is moving on just past the thing about the concept of the limiting nutrients. We're going to talk about the Carlson Trophic Index status. And this is just a status, it's an index of how productive a lake is. So the more eutrophic a lake, the more productive it is. Remember, eutrophication isn't necessarily a bad thing. You can have natural eutrophication, which is the natural filling in, the natural productivity of a water body, versus man-made eutrophication. You know, when we sort of pour tons and tons of sewage into a system, that's going to be man-made eutrophication. Natural eutrophication has to happen because that's part of the life cycle of the lake. Okay, so the Carlson Trophic Status Index is basically an index that's based on a log scale. So if you increase in 10 units, you're going to double your algal biomass in the water. So you go from 10 to 40, you're actually increasing your algal biomass by 4 times. Okay. Carlson Trophic Status Index is based either on Secchi discs, and you can see that on chlorophyll, on phosphorus, or sometimes they take an average, but usually they measure one of those things: Secchi disc, chlorophyll, or phosphorus itself, or basically active phosphorus. Okay, and the idea there with the Secchi disc is, if you're measuring a trophic status with the Secchi disc, you better be sure that you don't have a lot of inorganic particles entrained in the water as well. So usually you're going to take these measurements in the summer, sort of in the growing period. You're not going to take them in winter, because if you go in the winter, that's when you've got your big storms and the rivers are full of mud and silt and stuff. You don't want that. You want to measure that Secchi disc, you want to measure how much algae there is. So that's kind of important. You know, those linear regressions, I'm not sure where they come from. but those again are just rules of thumb. The trophic status, let's have a look at it. Basically less than 40, it's going to be oligotrophic. So whether you're measuring it by phosphorus or secudisc or by chlorophyll, chlorophyll probably would be your best endpoint. Less than 40 is going to be oligotrophic. Greater than 70 is going to be just horrendous. Okay, greater than 70 is going to be 6 to 10 times more algae in the water than an oligotrophic lake. And that's going to get kind of ugly pretty quickly. Okay, so that is just sort of an index, a management index that you would have. These regressions or these relationships here show chlorophyll versus secudisc depth, and this was actually done by Jeannie Itzen. She did a PhD for a guy called Hank McKellar over here several years ago. But it's kind of interesting over here. This is your secudisc depth, and this is your total phosphorus in microgram or milligram per liter. No, it's microgram per liter. And you notice it does this, okay? So why would it be more sensitive at lower total phosphoruses than up here? Kind of goes to that exam question that we had some time ago. It's not a linear relationship, it's a logarithmic relationship. Well, basically what happens is at very low concentrations of total P is going to be your limiting nutrient, okay? So as you add the marginal addition of total P, it's going to have a huge impact. It's going to have a huge impact on your chlorophyll, okay? But it gets to the point where your chlorophyll now is going to be interfering with light. Your phosphorus now is going to become relatively more and more abundant. Therefore, your response of your plants in the water is not going to be high. And you might get to a point over here where all of a sudden you're not phosphorus dependent, but you're nitrogen dependent. But it might be that also at this, if you get down to this point, you're also finding that, in fact, your light becomes the most limiting thing that goes on there. Okay.
Sorry, I have to run.
No worries. Well, we're just about done. I've got a few slides left, and then I'm going to let these guys go as well.
Paperwork, and I'll see you on Monday.
All right. See you later.
Thanks, guys.
Bye-bye. Okay. So let's go have a look. There's something called the hypolimnion. Actually, that was one of the things that I didn't put in the earlier slide. So the hypolimnion is this portion at the bottom of the lake that is more or less in direct contact with your sediments, okay? And so there's a specific response of the hypolimnion to certain things. In oligotrophic lakes over here, okay, and remember those profiles that we had in oligotrophic lakes? Because you don't have much, in an oligotrophic lake, you don't have that much biologic activity at the bottom, okay? So therefore, your O2, let me just do this over here, oligotrophic, eutrophic. Okay, now this looks like deep chemistry, but it's not really. It's pretty logical. We're just going to look at oligotrophic. Oligotrophic, think Lake Tahoe. Eutrophic, think Lake Victoria. Green and slimy versus beautiful, deep alpine lakes. Okay, oligotrophic. First of all, our oxygen over here. There's very little activity, benthic activity over here in terms of consumption of organic material. So we'd expect our oxygen here to be what? High, yeah. Okay. VO2, phosphates. There's not going to be much in the way of phosphates down there, okay? So that's, because it's an oligotrophic lake, it's going to be low. Ammonium is only really formed in anoxic conditions. So, low or none. You're definitely not going to have much hydrogen sulfide. And ferrous ions are formed in reducing conditions. If you've got a high oxygen, this is an oxic condition, a very high oxygen. It's not going to be a reducing situation. So any of your ion, in this case, you'll have low or nothing. Most of your ions, in fact, will be in Fe3+, which is insoluble. Fe2+ is highly soluble. So in an oligotrophic lake, you're going to have high DOs, low to no phosphates, low to no ammonium, low to no hydrogen sulfide, and low to no Fe2+ ion in the 2+ state. You go to eutrophic lakes, and it's going to be very different. A eutrophic lake, you're going to have all sorts of critters eating away, decomposing that organic matter. The first thing that drops out of sight is going to be O2. So you're going to have very low O, as a result, let me try and remember the logic over here. In reducing situations, the phosphates in the water are going to be solubilized. So phosphates become more soluble in these reducing conditions. Because there is no oxygen in the water, so instead of having nitrates and nitrites, there's no oxygen around, so we would have high ammonium ions, and the same thing here, hydrogen sulfide. If you smell kind of a hydrogen sulfide smell, you know it's going to be an anoxic condition. So H2S. And because there's no oxygen, there's a low oxygen, it's highly reducing. Fe3+, which is insoluble, gets converted or reduced to Fe2+. So Fe2+ is soluble. If I put my sonde down here, would I expect a higher conductivity for my oligotrophic lake or my eutrophic lake? Everything else being equal.
Eutrophic, because of all the soluble.
You got all these guys all of a sudden very soluble. So you would, for a given temperature, yeah, you'd find this. And you're probably also going to find a whole bunch of carbon dioxide down here as well. So yeah, that's basically it. And if we go again onto lakes and stuff like that in the summer, you drop that sonde down. The closer it gets to this hypolimnion, you actually often begin to see spikes in electrical conductivity. And that's because of this thing and, of course, your inorganic carbon. Inorganic carbon should be here. If you had inorganic carbon over here, it would be very high, okay? If you were considering that, where it would be low here. Okay? So that's the hypolimnion responses. Don't know if we'll see that next week just because it's so darn cold. But we'll see. All right. We've kind of gone through this already, but you'll see there's a slide that kind of explains that. So essentially what we know of in terms of man-made eutrophication is the more man-made eutrophication there is, the more slime there is. And I've been on Lake Victoria where all we've been able to see on the surface is algae kind of floating on the surface for as far as the eye can see. And, you know, the locals there are kind of like, what's happening? Tell us what's going on, you know, and they're scared to go down and get the water because, you know, you can't see through it. The first 2 inches is just scum. And then below that is still green and nasty and stuff like that. And of course, when that settles down to the bottom, you get these burps and you get sulfur dioxide smells and that kind of stuff. So a man-made eutrophication, when it's really, really bad, it's something pretty scary to actually see. So just a couple of things over here. In terms of the kinds of eutrophication we see, I've really spoken about open water algae, but you also have something called attached algae, which is the periphyton. So you have algae attached to rocks and other plants as well. And then you have higher macrophytes as well. Now, if you want to go to sort of in South Carolina, if you want to go to the Typhoid Mary of where you have eutrophication and lots of macrophytes generated, go down to Goose Creek. It seems like everybody and his brother goes down there, you know, boat propellers, people throw out their aquariums there. And basically what happens there is, in a eutrophic situation, you can have macrophytes which are invasive aquatics. And they will cover the surface of that lake in no time flat. So giant salvinia is like really, really bad. Another one is Brazilian water hyacinth. So these are all very, very pretty ornamental plants, but they get out of hand quickly in warm situations and with a lot of nutrients, and then they just kind of get out of hand. So there are some ponds on farms and stuff like that that eventually become completely covered. And what happens is it's usually a monoculture, and only one of those species will predominate, and it will shut down all of the natural species. And when it does that, you lose your habitat for your fish, you lose your habitat for your macroinvertebrates and other invertebrates, lose your habitat for birds and other things that live on the soil. Not the soil, on the water. Okay. Let me have a look. Photosynthesis and respiration, effects on routine water quality parameters, generally no effect on temperature. Yeah, we've kind of done all of this already, so there's no point in going over it again. There's a thing of natural versus cultural eutrophication, which you've seen there, and we've explained that as well. I guess what I liked about this kind of last word over here was that, you know, if you have phosphorus in a lake, this is like the fourth last slide. If you have phosphorus in the lake and it's 100 parts per billion, that's considered hypereutrophic. It's like, dude, you know, there's algae all over the place. But in Coca-Cola, you know, you can have thousands of parts per million and it tastes great. So phosphorus itself is not poisonous to us, but it's great for growth of these things, and that's not the poison, you know. And a lot of people kind of make it out to be some kind of poison, but it just stimulates growth, okay? Lake nitrogen, if it's greater than 500 parts per billion, it's high. but we can take up to 10,000 parts per million and more as adult humans. Blue babies get problems when it's above 10,000 parts per billion. I thought it kind of interesting about the lake mercury and PCBs, and I think that really has to do with this whole idea of biomagnification that we talked about a little bit earlier. Okay, I think that's about all that I wanted to cover in lake ecology. I think it's a lot better when we go out onto the water and we have a look at it there. So I'm hoping that next week we have a little bit more temperature in the water and we can see what the lake does for us.
Do you usually see any stratification on this?